Okay, so the next part of the discussion here is, if you go to the structural aspects of hydrocarbons, of alkenes, and alkynes. Structural aspects of alkenes, and alkynes. So here, if you are going to take the alkenes in particular, if you take alkenes, in alkenes, if you take hydrocarbons CH4, C2H6, C3H8, C4H10, all these comes under the molecular formulae. All this comes under molecular formulae. So if you take this methane, if you want to write the structural formula of methane, structural formula or formulae, if you go for methane, you can write the methane structure as, because carbon is tetravalent, first you highlight the 4 covalent bonds for each carbon and you look after the number of adjacent hydrogens. The number of adjacent hydrogens are 4. So this is the structure of methane molecule. This methane molecule, because it is having a tetrahedral plane, if I give the tetrahedral plane, this is tetrahedral shape. It has tetrahedral shape, and its bond angle is 109 degrees 28 minutes. Likewise, if you go for C2H6, this is ethane. C2H6 is ethane, and CH4 is methane. If you go for C2H6, then you can take the structure as first, second, third, fourth. Take the tetravalency of each carbon, again join another carbon, again show the tetravalency of the carbons, 1 2 3 4, 1 2 3 4, again attach all the hydrogens. So you find that here there are 6 hydrogens with 2 carbons. Again, each carbon is again tetravalent. Here each carbon is again tetravalent. Tetravalent molecule, tetravalent, and its shape is tetrahedral shape. Likewise, you can also take, that is C3H8. If you go for C3H8, you can take the structure, take 3 carbons, attach the valencies, just like catenation property of carbon. There are 3 carbons. First satisfy the tetravalencies for each carbon. Each carbon is having 4 covalent bonds. First carbon 1 2 3 4, second carbon again 1 2 3 4, third carbon 1 2 3 4. Then you check the total number of hydrogens. We have 8 hydrogens, so attach 1 hydrogen here, 1 hydrogen here, 1 hydrogen here, 1 hydrogen here, hydrogen, and hydrogen. You can see that the length of the carbon chain is 3. There are 3 carbons, so length of the carbon chain is 3. Likewise, if you go for butane, that is, if you go for butane, I think I can write, you can show here butane C4H10. If you take, this is butane. If you go for butane, then you can take number of carbons are 4. So immediately 1 2 3 4 satisfy. This is called carbon skeleton. First you have to show the carbon skeleton. When you are showing this carbon skeleton, attach each carbon with the covalent bonds, then you satisfy the rest of the valences of each carbon. First carbon is tetravalent, so 1 2 3 4. Second carbon again tetravalent, 1 2 3 4. Third carbon again tetravalent, fourth carbon also tetravalent. This is called skeleton of the carbon, and it is also giving the straight chain. If it is giving straight chain, then you also check the total number of hydrogens. Number of hydrogens are 10 hydrogens here. Molecular formula is C4H10. It has 4 hydrogens and 4 carbons and 10 hydrogens. So you can take all the hydrogens and adjust it with the covalent bonds of carbon. Covalent bonds of carbon. So here all this comes under the structural aspects of the alkanes, and these alkanes sometimes they also show isomerism. Isomerism. What is isomerism? Isomerism of an hydrocarbon is the property in which has same molecular formula, but differ in structural formulae. For example, for alkanes, if you take butane, C4H10 is butane. It can give two different types of isomers. One is it can give chain isomer. What are chain isomers? Pair of isomers which differ in the straight chain or in branched chain. So if C4H10 can be written in two different formats, 1, 2, 3, 4. This is straight chain. If it is a branched chain, it can give one branch like this. This is one branch. If you want to show this in bond line representation, there are 4 carbons. 1, 2, 3, 4 carbons are there. So 1, 2, 3 and 4. This is also straight chain only. If this is branched chain, then you can show 1, 2, 3 and 4. Here it is very clear. Here the branch is very clear. Branch is very clear here. This is the branch. Here it is straight chain. This is a straight chain actually. This is a branched chain. You can see the branch curvature. So you can call this as, because it is a branch, wherever branch is there, you can add a prefix iso. Isobutane. It is a straight chain. So simply you can say normal. N stands for normal. N means normal. Normal butane. Normal butane. So satisfy the tetravalencies now for each carbon. Satisfy the tetravalencies. So you can take here hydrogen, hydrogen and hydrogen. Here also you can take hydrogen. Here also you can take hydrogen, hydrogen, hydrogen and hydrogen. And here you can take hydrogen. For isobutane, yes. For isobutane, there is only one bond here. So therefore you can take 3 hydrogens. Again one bond, 3 hydrogens. 3 bonds, take 1 hydrogen. 1 bond, again take 3 hydrogens. This is isobutane. If you want to expand this isobutane, still you can expand. That is, you can take here 1, 2, 3, 4 carbons. Again 1, 2, 3. 1, 2, 3. Here only 3 bonds are there. So 1, 2, 3. 1, 2, 3 hydrogens, 4 hydrogens, 5 hydrogens, 6, 7, 8, 9, 10. This is isobutane. You can see here, this is the branch. You can able to notice here. This is isobutane. This is the branch. This is isobutane. Okay. This is isobutane. So all these are the structural aspects of the alkanes. Likewise, we will also study the structural aspects of the alkenes with their molecular formula of the compound. Just like in the case of alkanes, alkenes also will show the property of isomerism, and we will study what isomerism it can show in the case of alkenes. Okay, so the next part of the discussion here is the structural aspects of alkenes. Structural aspects of alkenes. If you go for the structural aspects of alkenes, the simplest alkene is C2H2 is the simplest alkene. Next higher alkene is C3H4 and the next higher alkene is C4H6. C2H6 is ethine, root word is eth, and because two carbons are there, so root word is eth. C3H4 propane, because the number of carbons are 3. C4H6 is butane, because the number of carbons are 4. So what we are noticing here is, if you take the structural aspects of acetylene, if you take acetylene, this is A, this is B and this is C. If you go for A, C2H2, take the structural aspects, write the skeleton of the C2H2. So if you take carbon, because there are two carbons, attach one single bond, then there are two hydrogens. So first you satisfy the tetravalency of the carbon. So because it is an alkyne, it's an alkyne, sorry, this is alkene I have written, so this will become alkyne, because it is an alkyne. If it is an alkyne, then compulsory between the two carbons there should be a triple bond. If it is triple bond, then you can find that between two carbons compulsory there should be a triple bond, and you have only two hydrogens, so place one hydrogen over here and place another hydrogen over here. If you go to the shape of this alkyne, that is acetylene, you can just take, it is a linear shape structure, it has a linear pattern, so it's like this is linear shape, bond angle (180°). So suppose if you can take here the same structure as carbon triple bond, hydrogen, so here the bond angle is 180° between carbon and hydrogen, bond angle is 180°, and here between two carbons there is a triple bond. This is a triple bond, which is an important characteristic feature of the alkynes. Similarly, you go for C3H4, next B, go for C3H4. If you go for C3H4, there are three carbons, 1, 2, 3. Because it's an alkyne, between any two carbons you create a triple bond, and here you satisfy the tetravalencies of each carbon. Here also triple bond, then single bond hydrogen and hydrogen. So what we are noticing here is, again we have a triple bond between two carbons, or you can simply write this as CH3 single bond, carbon triple bond, single bond hydrogen. This is the expanded form of the structure of propane, and this is condensed form of the structure of propane. Or you can write the same structure as, if you consider each methyl group as one dot, there are three carbons, 1 to 3, there is a triple bond, so here one bond is there and here one bond is there. This is the bond line representation of the alkynes. Here there are two carbons, here also you can show the bond line representation. There are two carbons and in between there is a triple bond, so simply you can place it like this. This is the bond line representation. Each dot over here represents a carbon. Here one carbon is there, here one carbon is there, and here also one carbon is there. This is propane. Similarly, you go for butane. If you go for butane, that is C4H6 is butane, number of carbons are 4. You can create a triple bond between any two carbons. One is, you can take 1, 2, 3, 4. You can create a triple bond over here. Next, 1, 2, 3, 4. You can create a triple bond over here. So what is happening? These two structures also they are going to give the isomerism. Alkynes gives isomerism just like alkanes. Here you can see that if you want to satisfy the tetravalencies, Here we have 3 bonds. For the first 2 carbons we have 3 bonds, triple bond. So satisfy the tetravalency, attach one single bond over here and take one hydrogen. Here come back to this hydrogen, come back to this carbon, it has 2 covalent bonds. So satisfy the tetravalency, attach 2 more covalent bonds and place the hydrogens. Here again one single bond is there over here. So place 3 hydrogens and satisfy the tetravalency of the carbon. You can see that there are 4 carbons and 6 hydrogens. So if you look into the chain, 1, 2, 3, 4 carbons, there are 6 hydrogens, 1, 2, 3, 4, 5 and 6. This is the expanded structure of the butane. Still, if you want to write the structure of butane in the same format, condensed structure also you can write CH3 single bond, CH2 single bond, carbon triple bond, single bond hydrogen. So this is one structure of that is butane. Now we can call this as butane because here the triple bond is located after the first carbon. Immediately after the first carbon, here the triple bond is located. Then again second, third carbon and fourth carbon. So you can call it as 1-butane. 1-butane. Now go for the second case. Here the triple bond is located in between the 2 carbons. It is in the middle of the chain. So you can start from the left side or you can start from the right side if you want to give the numbering. So you can just take, suppose you first satisfy the tetravalencies of each carbon. So take hydrogen, single bond, hydrogen, again single bond, hydrogen. Already 4 bonds are there for this carbon, 4 bonds are there for this particular carbon. Go for the terminal carbon, 1, 2, 3. So you can see again number of hydrogens are only 6, but the triple bond is in between the longest chain. So or you can write this as CH3 single bond, carbon triple bond, single bond CH3, because the triple bond is located in between carbon chain. So you can start the chain from any side, either from left side or from right side. So this is 1, this is 2, this is 3 and this is 4. So because you are starting from the left side, the triple bond is located after the second carbon. That is why here you can say 2-butane. 2-butane. So 1-butane and 2-butane. Therefore, we can come to one conclusion: 1-butane and 2-butane. 1-butane and 2-butane are positional isomers. Positional isomers. 1-butane and 2-butane are positional isomers. 1-butane and 2-butane are positional isomers. So next part of the discussion, next structural aspects of hydrocarbons, that is structural aspects of alkenes. If we go to the structural aspects of alkenes, the simplest alkene is, that is C2H4 is the simplest alkene. This is ethene. C3H4, this is propane, and C4H6 is butane. So if you take here, if you are taking C2H4, we take the structural aspects. There are 2 carbons, so I am taking 2 carbons. Satisfy the tetravalency. You place a double bond between 2 carbons, and there are 4 hydrogens. So first hydrogen, second hydrogen, third hydrogen and fourth hydrogen. What you are noticing here is between 2 carbons you find that there is a double bond. That's why it's an alkene. So if you take the shape of the C2H4 molecule, yes, it's a planar molecule. It's a planar molecule. The shape is planar. It's a planar molecule. So if you go for B, C3H4, if you take it is propane. This is propene. If you take propene, yes, you can take 3 carbons, that is 1, 2 and 3. You can create a double bond anywhere, either between these 2 carbons, or you can create the double bond between these 2 carbons or these 2 carbons. So I am creating the double bond between the first 2 carbons from the right side to the left side. So here, if you take, because every carbon is tetravalent, so again you add 2 bonds here. Here we have 3 bonds, so attach 1 more bond. Here we have only 1 bond, so you take another 3 more bonds. Hydrogen, 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 hydrogen. Here 1 hydrogen, and here also 1 hydrogen. So therefore here this is nothing but propene. So you can just write here, or simply CH3 single bond, CH double bond, CH2. You can see that there is a double bond between, in the longest chain of the carbon you are finding that there is a double bond. That's why we can call this as propene. Propene. 3 carbons, prop, double bond in. So propene. Go for the next case, that is C, butene. C4H6 is butene. If it is butene, then you can take here, that is 1, 2, 3, 4. Yes, it can give the chain isomerism as well as positional isomerism. So you can take here, you can create a double bond between first 2 carbons, and you can place 2 bonds here, attach 1 bond here, attach 2 bonds here, and attach 3 bonds here, and satisfy the tetravalencies. 6 hydrogens, so 3, here 2, this is C4H6, yeah, already 5, so here 1, 2, 3, 4, 5, 6, C4H8, sorry, this is C4H8, 5, 6, C4, C3, this is C3, C3H4 is propene, so this is C4H8, so this is C4H8, so if it is C4H8, number of hydrogens are 8, yes, so 1, 2, 3, 4, 5, 6, 7, 8, so this is butene, the structure of butene, or you can just simply write it as, that is CH3 single bond, CH2 single bond, CH double bond, CH2, or you can write here, or you can write the same butene as, that is CH3 CH double bond, CH CH3, or you can show the bond line structure as first carbon, second carbon, third carbon and fourth carbon. You are finding a double bond 1, 2, 3 and 4. So you are finding the double bond between second and third, so you can create a double bond between second and third carbon. Here also you can show the bond line representation. If you want to show the bond line representation, 1, 2, 3 and 4. Here the double bond is between first and second carbon, 1, 2, 3 and 4, first and second carbon, so you place a double bond here. So this is bond line representation of bond line structure of 1 butene, bond line structure of 2 butene. So therefore we can come to one conclusion saying that 1 butene and 2 butene, 1 butene and 2 butene, 2 butenes are positional isomers. Positional isomers. You can also prepare one cyclobutane. You can also prepare cyclic structures. Suppose for example, for same C4H8, you can prepare a cyclobutane. Number of carbons are 4, so take 4 carbons, 1, 2, 3, 4 carbons. There are 8 hydrogens, so you can take here 2 hydrogens, you place over here 2 bonds, here 2 bonds, here 2 bonds and here also 2 bonds. So you can take here So this is the structure of the cyclobutane, or you can simply write this as CH2 single bond CH2 single bond CH2 single bond CH2, or you can simply show the bond line structure as the cyclobutane like this. Each corner it has one carbon provided. Each corner it has one carbon provided. Here one carbon, here one carbon, and here one carbon, cyclobutane. So like this you can prepare the cyclobutane, because you find all single bonds here. Or you can take the same structure, that is bond line structure of cyclobutane, bond line structure of cyclobutane. Each corner is having one carbon, and this is automatically understood as cyclobutane. Two hydrogens are hiding at each carbon. It's a bond line representation. In bond line representation, we only highlight the number of carbons at the four corners of the square, and for each carbon, two hydrogens are hiding in that particular plane. So the next part of the discussion here in organic chemistry, that is hydrocarbon of organic chemistry, is nomenclature of organic compounds. So in this nomenclature of organic compounds, if you go for an organic compound, you take an organic compound. An organic compound is made up of a root word. Root word represents number of carbons. Then an organic compound is made up of primary, suffix. When you say primary suffix, it is, we can take in terms of with respect to, when you say primary suffix, you can take it as "-ine", you can take it as "-ine", you can take it as "-ine". "-ine" stands for alkenes, "-ine" stands for alkenes, and "-ine" stands for alkynes. Apart from this, it is also having the second, after primary suffix you can go for secondary suffix. Here 2 degree stands for secondary suffix. Secondary suffix actually gives the the technical name of the functional group. Secondary suffix is nothing but naming of functional group. Naming of the functional group. Then you can take the primary prefix. Primary prefix, it is used for cyclocompounds. And the last one is, that is numerical prefix. This indicates number of groups, number of substituents or groups which are repeating again and again in the same manner. Numerical prefix means, suppose for example you take, that is for a given organic compound, for an organic compound, okay, numerical suffix is mentioned in terms of di, tri, tetra, and so on. So for example, one example I would like to give you to make you to understand very clearly. One example I would like to give you. Suppose I am taking take one example. take one example, but 2 in 1 ol. Say for example, you are taking one organic compound which is having the IUPAC name. This is the IUPAC name. This is the IUPAC name. But 2 in 1 ol is the IUPAC name. So here the word but stands for root word. So therefore, if here but is the root word and in is the secondary in is not secondary, that is, sorry, this is primary suffix. It is primary suffix, and the ol is nothing but the secondary suffix. This is one example. That means here bit represents root word represents the number of carbons, in represents the primary suffix, whether it contains a double bond or single bond or triple bond, like that, and ol is the secondary suffix which gives the functional group. Root word represents number of carbons. This is example 1. Go for example 2. I'll give you much more simpler example. I'm going to give you much more simpler example. I'm going to give you, that is, suppose for example, but 2 in 3 ine. Suppose an organic compound whose hydrocarbon is given by the IUPAC name, that is but 2 in and 3 ine. So here cast the root word. In is the primary suffix. In and ine, both of them are primary suffixes. So suppose if you want to write the structure for both this, if you want to write the structure for this but 2 in and 1 ol and but 2 in and 3 ine, if you want to write the structures, for example, that is 1, 2, 3, 4, 1 ol. So for if you take the numbering 1, 2, 3 and 4, so this is ol means it is alcohol. So attach OH, then you says 2 in means after second carbon you create one double bond, 1 ol. Satisfy the tetravalencies. So attach one bond here, attach one bond here. 3 covalent bonds will come for the fourth carbon, and 1 covalent bond with hydrogen will come for the third carbon. Again 1 covalent bond with hydrogen for the second carbon, and 1 single bond hydrogen. This is bit 2 in 1 ol. This is bit 2 in 1 ol is a structure. If you go to the structural formulae of bit 2 in and 1 ol, that is, you can take 4 carbons, 1, 2, 3, 4, 1 ol. If you take 1 ol means 1 alcohol, attach one alcohol here, 1, 2, 3, 4, give the numbering. Then 2 in, after second carbon create a double bond, then satisfy the tetravalencies. So 1, 2, 3, again 1 covalent bond. Here already 3 bonds are there, so to take one more covalent bond. Here only 2 bonds are there, so attach 1 covalent bond here and 1 covalent bond here. So single bond hydrogen, again single bond hydrogen, single bond hydrogen, single bond hydrogen, single bond hydrogen, and single bond hydrogen. This is the structural formulae for bit 2 in 1 ol. Likewise, similarly, if you go for bit 2 in 3 ine, if you take 1, 2, 3, 4 and bit 2 in, so 1, 2, 3, bit 2 in 3 ine. So bit 2 in 3 ine means if you take here double bond 3 ine, so 3 ine means, I think bit 2 in, I can say this as, you better change it to 1 ine, not 2 in, because the condition doesn't accept or else you can take here, you change the root word here, instead of but you take pent, that is much better, and make it 3-ine, pent 3-ine. So pent 3-ine means I am attaching one more carbon. So 1, 2, 3, 4, 5, pent 3-ine with 2-ene, pent 3-ine. So this we make it as 1-ene, pent 1-ene, 3-ine. So you can take one double bond here and one triple bond after the third carbon. Root word is pent, so therefore satisfy the tetravalencies here for the fifth carbon, carbon single bond hydrogen, carbon single bond hydrogen, and carbon single bond hydrogen. Again here also already fourth carbon we have 4 covalent bonds, and the third carbon also we have 4 covalent bonds, and the second carbon we have only 3 bonds. So attachment single bond hydrogen, and here single bond hydrogen, single bond hydrogen. So this is the structural formula for pent 1-ene and 3-ine. So the next part of the discussion is, that is, let us study something about the nomenclature of organic compounds in terms of their functional groups, and writing the IUPAC names and their structures of the organic compounds. So based on that, here we can take class of organic compounds, class of organic compounds, then you can take functional group, general formula, general formulae, then you can take secondary suffix, and the appropriate example. So class of organic compounds, functional groups, general formulae, secondary suffix, and examples. So what I can do here is, let us start one by one. Suppose I am going with the first one, that is alcohols. The class of organic compounds are alcohols. Functional group is OH. Or you can just write it as, you can just show it like this. This is the functional group of alcohol with the oxygen. And general formula, you can take ROH. This is alkyl group, alkyl aliphatic alcohol. Secondary suffix is ol. Example, you can take CH3, CH2, OH, ethyl alcohol. Secondary suffix is ol, ethyl alcohol or ethanol. So this is alcohols. Go for the next case, that is ethers. If you take ethers, general form, functional group, ethereal oxygen, we call this as ethereal oxygen. Then general formula, R, O, single bond, R, secondary suffix, oxy. Example, we can take C2H5, O, C2H5. This is ethoxy ethane. So here you have a lone pair here, ethoxyethane. So let's continue. That is the next part of the discussion. In this, you are finding that the class of organic compounds are ethers. The functional group is ethereal oxygen, and this is dialkyl ether. You can name this compound as dialkyl ether, and the secondary suffix for ethers is oxy. And you can take these examples. First example is ethoxyethane, and the second example is, that is, here you are finding that there are 2 carbons, and here you are finding that there is only one carbon. That's why we can write the IUPAC name as, that is methoxyethane is the IUPAC name. So we have completed two classes of organic compounds. Next we'll go for the next part of the discussion, that is we can go for carbonyl compounds. In carbonyl compounds, A, that is we can take aldehydes. If you go for aldehydes, functional group, the aldehydes functional group is, okay, that is aldehyde functional group. We can take hydrogen single bond, carbon double bond with one carbonyl group. The aldehyde must and should contain CHO. This is aldehyde. General formula, you can take R, C double bond O of H. Secondary suffix is al. Example, you can take H single bond O of H. This is formaldehyde. And you can take one more example, that is CH3 single bond, carbon double bond, single bond hydrogen. This is acetaldehyde. Also called ethanol. If you go for next case, that is ketone, if you take the functional group is simply carbonyl group. So this is ketone. So here you can take R single bond, carbon double bond oxygen, R. Secondary suffix is non. Example, you can take CH3 single bond, carbon double bond, CH3. This we call it as, you can call it as acetone, or you can call it as 2-propanone. 2-propanone is the IUPAC name. 2-propanone is the IUPAC name. Ethanol is the IUPAC name. Methoxyethane is the IUPAC name. Ethoxyethane is the IUPAC name, and ethanol is also the IUPAC name. So we'll go for the next part of the discussion, that is next part of the class of organic compound. Let us assume that the compound is amines, functional group NH2, general formula is R NH2. Example you can take that is C2H5 NH2 with a lone pair on nitrogen. Okay, we can take, this is the example, and here secondary suffix you can simply give amino. Amino is the secondary suffix. Amino is the secondary suffix. So therefore, now what's happening here is, like take one or two examples. Examples you can take. Examples if you take. Examples if you are going to take here. In the examples you can take ethylamine, and you can also take, sometimes you can take aromatic amines also you can take. This is ethylamine. You can even take few more examples, like this is called amino benzene, or sometimes you can also call it as aniline. You can call this as aniline. So this comes under the class of compounds, that is amines. Then you can take next part of the class of compound, class of organic compound, that is you can take amides or acyl halides. You can take acyl halides. Acyl halides. Functional group C double bond O of X, where here X is the halogen. X is the halogen. Example, general formula, we can take R C double bond O of X, acyl halide. Example, you can take example CH3 CH2 carbon double bond chlorine. This is propanoyl chloride. Propanoyl chloride is the example which you can take. So likewise you can take one more class of compound, that is you can take, that is amides. General formula, carbon double bond oxygen NH2. This is the whole thing, the structure, call this as amide. General formula RC double bond O of NH2. Alkyl amide. Example, you can take CH3 carbon double bond oxygen NH2. Acetamide. So now after understanding the table with the class of organic compounds, then identifying their functional group, then writing their secondary suffix, giving the general formula and their respective example. Now let us do one small exercise in this organic compounds, that is, how many structural isomers are possible for the compound. The question is, how many structural isomers are possible? For compound pentane. So if you go for pentane, this is C5H12 is the molecular formula. If you go for the structural formula, the best thing is take the number of carbon atoms. The number of carbons are 5. Root word pentane. So this is pent. Pent is the root word and ane is the primary suffix. So now therefore what we can do here is, the number of possible structural isomers possible in the case of pentane are, I think it is 3. First we'll go with straight chain, 1, 2, 3, 4 and 5. Satisfy the tetravalencies, 1, 2, 1, 2, 1, 2, 1, 2, 3. Attach the number of hydrogens, 3 hydrogens, 2 hydrogens, again 2 hydrogens, hydrogen and hydrogen. So here this leads to, this is nothing but expanded structural formula of pentane. So the same thing you can write it as CH3 single bond, CH2 single bond, CH2 single bond, CH2 CH3. You can see in between the carbon chain you can find that the individual members, you can see one methylene group over here, another methylene group over here and another methylene group over here. These 3 methylene groups, these are called homologues. Repeat of same functional groups. FG stands for functional groups. FG stands for functional groups. So each homologue is behaving as a similar functional group. So what is meant by the CH2 group? CH2 group is a homologue. It has the same properties, same physical properties. It has the same physical properties, and it's a sort of repitance. Wherever the CH2 group is repeating, wherever the number of CH2 groups are increasing, the hydrocarbon also will increase in its carbon chain, and it will change in its properties. So based on that, what we can say here is, that is, this is pentane. This is first isomeric structure. This is first isomeric structure of pentane. I mean, for the molecular formula C5H12. Second isomeric structure you can take. Now I am going to create a branch. If I create a branch, then you get here, this is the branch I want to create. This is called isopentane. Isopentane. Satisfy the tetravalencies, CH3, single bond CH3, again 3 covalent bonds, so take one hydrogen here, again here CH2, and again here CH3. So if you want to write the IUPAC name, take the longest chain, 1, 2, 3, 4. This is going to become the substituent. So therefore 2-methyl butane. 2-methyl butane. So therefore we can, that means this is the first isomer, this is number 1, first structural isomer, this is second structural isomer, this is second. Go for third. If you go for third, I think we can go for the third, that is third isomer. If you take, you can create a cyclic branch like this, CH3, CH3, CH3. This is called neopentane. Neopentane. Write the IUPAC name, 1, 2, and 3. So on the second carbon there are 2 methyl groups. Here 1 methyl group, and here also 1 methyl group. So therefore 2,2 dimethyl propane is the IUPAC name. 2,2 dimethyl propane is the IUPAC name. So therefore the answer for this question, the answer is the total number of structural isomers is equal to 3. Those are N-pentane, isopentane, and neopentane. 3 isomers are possible: N-pentane, isopentane, and neopentane. 3 isomers are possible.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.